In the previous video, we walked our way through the Sigma placement grid and built the case for the existence of 4 types of mathematical thinking. We also, at the end, gave you some ideas about how to group students to make for a powerful mathematics classroom, in particular, grouping students in group 1 and students in group 4, and grouping students in group 2 and students in group 3. And I tried to give you some ideas in terms of why this is a powerful method. Now, when we think about how we might start going forward from here, one of the features that always crops up is, well, how can we really get a good way of measuring and documenting these 4 types of mathematical thinking? And at this point, a very powerful tool is the problem-solving board. This goes back many years to a chapter that I did on metacognition, and it deals with how one thinks about the thinking process itself. So when we think about the problem-solving board, it was initially designed as a data collection instrument. It was designed to help us get better insight in terms of how people are thinking as they go through and solve problems in mathematics. And by people, I mean little people from kindergarten through 6th or 7th grade. So this whole approach proved itself to be very, very powerful. And it gave us a tool that could be used not only to measure and assess problem solving and metacognitive thinking, but also it turns out to teach problem solving and metacognitive thinking. So I'm going to present this in both of its uses here as an instrument that you can use as part of the Sigma placement grid to determine each of those 4 groups. And then also as a teaching tool, because what we find is that it becomes both a record of action and the object we act upon, much the same way that the fraction grid served that dual function when we were thinking in that perspective. So the problem-solving board has an interesting history in that it was initially designed as a data collection instrument, and it was almost after the fact that we discovered how powerful it was in teaching problem solving and enhancing students' metacognitive thinking in mathematics. It turns out that it goes back even further. And what you will find as teaching professionals is you're going to be given a lot of opportunities to learn about how to teach and enhance problem solving. This is a huge area, as you might guess. And most of the problem solving strategies and methods that you will be experiencing go back to Polya. Polya was probably one of the initial thinkers in this area in terms of how one goes about solving problems in a classroom setting in mathematics and in science and in engineering. And whether or not the leader of the in-service will tell you the most commonly used source that they'll reference is Polya's How to Solve It. I've given you the citation here so you can take a look at it on your own if you choose. Half Price Bookstore on occasion will have these relatively cheaply, or you can go and Google it online. But Polya really has a lot to say about mathematics teaching and how you can go about enhancing it for your students. Here is what Polya told us about problem solving. And if you have gone to school in the Houston area, I'm sure you've heard these 4 at one point or another. This is the cornerstone for almost all of the problem-solving workshops that I've seen through the years. Basically, Polya breaks problem-solving down into 4 phases. And the way he described them was, first you understand the problem. We'll talk about what this means in math speak here in just a minute. But first you understand the problem, then you devise a plan to deal with the problem, then you carry out the plan, and then you look back and evaluate the effects of your work. So let's translate this into math talk a little bit. When we talk about understanding the problem, This includes labeling and identifying the unknowns, the conditions, you know, the if then else that you have to deal with, the starting point and end points like the horse problem had us work with, what the data was, what are the numbers, what do we understand about it? Is it soluble? For example, if you have a problem that requires you to divide by 0, that's not soluble because division by 0 is not something that we're allowed to do. And then when we talk about devising a plan in POLIA, this is really fairly elaborate. You have to draw upon your prior knowledge. You have to frame techniques and methods and processes and procedures. Sometimes you even have to restate the problem. And it's at this level that you have to really pull from your metacognition. You have to think about your thinking to design the plan. What we've found through a lot of research is that by the time you understand the problem and you devise the plan, you've really done most of the heavy lifting at that point. Because once you carry out the plan, that's basically procedural. And we have the opportunity to use computer technology, calculator technology. It's almost done by the time you understand and devise your plan. The final checking phase from POLIA would be checking the correctness of your solution. That would be the first part of the Sigma grid, wouldn't it? Did you get the correct answer or not? And then adding this problem to your store of knowledge so that you can think about it when you solve future problems. And it turns out that POLIA has some real strengths here. In particular, it's a very generalizable approach towards problem solving. And in fact, you could probably use it. I'm stepping out of math for just a second here. You could probably use it for any situation in your life where you have a problem. It's really powerful, and you can apply this type of problem solving approach to many, many different types of problems. Now, what POLIA has suggested, and what I'll certainly support, is that this framework should be applied often and in many different situations so that your students can gain experience and develop their confidence in problem solving. And POLIA's given some nice quotes. I'm not going to read through these. You can come back to this chart. You notice that this shows up in your Blackboard shell. You can read this, but you'll probably see these in your workshops on problem solving in the future. Now, as it turns out, the method does have some weaknesses. POLIA works really well in developing problem solving if you have students who have already had experience with problem solving. The downside is if you have students who don't have a clue about how to go about solving problems, this approach becomes very difficult for beginners to grasp, and in part it's because it's mistaught. In many of the curriculum materials you'll see, you'll be given a unit on how to teach problem solving, which basically has the students memorize the 4 steps of POLIA. That's not too helpful. You have to experience the 4 steps of POLIA. What we find is that when this memorization of the steps is followed, students either get lost in these steps or they don't consider the interactions because they've never really had to think about them. So with this as a background, the problem solving board turns out that as it was designed, we really did try to put POLIA into practice. That was one of the design criteria when this was developed. And I set it up in such a way that it provides a graphic framework, because knowing what we know about fractions, for example, if we can have something that is both object and record of action, it turns out to be extremely powerful. So that was one of the pieces I wanted to be in place here, was that this was both object and record of action. So let's take a look and see what it looks like. Here's the problem solving board. And you'll notice that it consists of some areas where we can record our work. So yes, it's a framing device, all right? It frames out different questions and different approaches, and it gives you a place to work. And as you put your work forward, you're building a record of action. This template becomes the object we act upon when we're doing problem solving. It also serves as a record of action of the problem solving experience itself. And I'll give you some student examples here towards the end so you can see how that plays out. You'll notice that these are put forward in terms of some very simple questions. And if you think back to our numerical fluency approach, remember those were simple questions also. In this case, the questions are, what do we know? What does it look like? What should we do? And then two statements, solve it, or do it, dang it, right? And then check it. So let's take a careful look at Polya's phases and see where they can be found on the problem-solving board. I think we'll find that's rather helpful. When we talk about what do we know, that's really Polya's approach towards understanding the problem. And in order to make use of mathematical modeling and representations, you'll notice that often we have to draw sketches, and we have to use physical manipulatives, and we have to perhaps use a spreadsheet, and all of these different approaches. And so what we start off with as we come to understand the problem, this is where we identify the data, where we identify whether it's even soluble or not, whether we think about how would we go about solving this problem, just in general. What are the interactions? What type of problem? Is it whole number? Is it fraction? Is it geometry? When we set up what does it look like, this is furthering our understanding of the problem. And I would encourage you to think about this as being where we bring forth the mathematical modeling. Here's where we use the manipulatives to show what the problem looks like. Here's where we'll set up the number lines, the area models. Here's where we'll set up our fraction charts. You'll see a couple examples where you can really see what this is like. Basically, any representation the students understand. If it's a spreadsheet representation, if it's a table, if it's a graph, if it's a chart, this would go into this section and it would be sketched in on the problem solving board. Once we've gone through the steps of understanding the problem, we then do what Polya would call devising a plan. And you see how the question hits that, don't you? What should we do? Well, as you answer that, you answer it in terms of devising a plan. And then you do it, dang it. You carry out the plan. And after you carry out the plan, you check, you look back, and we'll see what that means. It's not just checking for a correct answer. Rather, did you get the correct answer? And can you show by some mechanism that you really understand what's going on? That should be familiar to us now, thanks to our thinking about the Sigma grid. So here's a couple student examples that I think are helpful for us as we explore this a little bit. These came back from what used to be called the summer boot camps for people who didn't pass the end of year exams. This particular group of students were 5th graders and going into 6th grade. And so you can tell up front, they didn't have initial success, but they were able to get success thanks to the problem solving board. And so as we look at this, here is what we start off with. We have a question or a topic that we're going to have the students think about. And we want to be a little bit cautious here that these problems actually are problems. One of the things that is not effective is to waste this on something that's trivial. If it's a trivial question, it should be memory recall and is memory recall. If it's something you have to stop and think about, if it's a true problem for the students, that's when you want to break out the problem solving board. That's when this is most effective. So let's read the text here. And what's interesting, I think you'll find, is all of your old reading comprehension strategies work very, very well with the problem-solving board. This should make sense. Dr. Campione and Dr. Brown were both literacy and reading people, whereas I am more of a math person. So that's where this overlap plays out. So let's read this. There's 156 fifth graders and 148 sixth graders at the track meet. There were 18 teachers helping time the races. How many students participated in the track meet? And so when we talk about what do we know, one of the things that we know is we know there was 156 fifth graders. There was 148 sixth graders. You notice we did not put down 18 teachers. The student recognized that that was extraneous information. Not every piece of information is going to be used. And in a good problem, quite often you'll include extra information so that you will learn how to identify what's important in solving the problem and what is not. We also know that we're trying to get a total of some kind, and to get that total, we add. So here the student has done a very, very nice job of laying out the important information, the goal of what we're asking for, and how you're going to go about doing it. Now, what does it look like? Now we're going to start seeing now how this can help us identify whether you really understand what's going on or not. Could the students select a mathematical model that models the problem that's given to them? And in this case, they did. You'll see what they're using here is they're using a modified version of a number line. And they're identifying what the fifth graders component would be, what the sixth grader component would be, and how you would show the total. Hopefully from our work with fact families earlier, you will recognize this way of representing addition on the number line, and you'll see that the student indeed did represent the problem appropriately. Now, when it comes to devising the plan, there's kind of a subtle little piece to this that I want to emphasize. In particular, it's important that the students record a complete thought in complete sentences, not just add. Add doesn't tell you what to do. You notice the way this is written out here. It's a complete sentence. We add 156 fifth graders and 148 sixth graders to get the sum of how many students went to the track meet. Now with little guys, you're going to have to record this for the students. You'll ask them and they'll tell you what to do. And when you write it for them, I'm thinking grades K through 2, for example, you'll want to record it in complete sentences. When we think about this linguistically, we can understand why. Remember the process concept or the noun verb aspect of understanding. We have to have the object, we have to have the process or the action that we act upon that object. In math talk, we have to have the mathematical concept, and we have to have the action upon that concept. When you write a complete sentence, you write both noun and verb components linguistically, and so it almost guarantees that you're addressing both the concept and the process, or both the object and the action. Then you do it, dang it. And as you do it, I would encourage students to record their units. When you do miles per gallon, for example, by keeping the units in mind, you can have another check to see if you've done it correctly. So solve it. We do it, dang it. How do we know? Well, we'll go back and we'll check. And one of the easier ways to check based on our understanding from fact families is to do the inverse operation. You check addition by subtraction. You can check subtraction by addition. You can check multiplication by division, integration by differentiation. I mean, you have all of these ways of checking. And the first step is to do the check using the inverse operation. But you want to do a little more than that. In particular, you want to make sure that this picture, the what does it look like, accurately models the mathematical situation from the problem as filtered by what we know as being relevant. We also want to make sure that it models the plan based on what it is we say we are going to do. We also need to make sure what we say we're going to do is actually reflecting the situation. A rather funny little situation occurred once. We had a story about a boy going to the 7-Eleven and buying a hamburger. And of course, you know, you have the different prices for hamburger and fries and drinks and so on. And so the students had an open-ended task where they were asked, how much could you buy for $5? And oddly enough, the answers that they came up with were answers like 77, 4, 18. And of course, we wondered, well, what on earth? Where did these come from? And what they did is they took the numbers 7 and 11 from the 7-Eleven store and added and subtracted and multiplied those numbers together. And when we asked why, they said, well, those were easy numbers to work with. And it never occurred to them that there was another goal to the problem. So quite often what will happen is you'll have students who are able to identify and even draw, but when they plan, they'll do something easier rather than thinking about what's the correct answer. That's kind of an extreme example, but when it showed up, it was pretty eye-opening. Here is another student example that's kind of interesting. This goes, you can almost see how old this is, can't you? We're talking about televisions weighing 34.5 kilograms. You know, TVs now don't weigh that much. Computers weighing 17.5 kilograms, kind of showing our age a little bit here, but you'll see what's happening. What is it we know? In this case, you've got 4 boxes at 17.5 kilograms. You're going to have to multiply. You've got 3 boxes at 34.5 kilograms. Again, you're going to have to multiply. In order to find out how much weight did Mark move, you're going to have to add those together. And here is where we see the what does it look like start to show itself. Here's where we can decide on that sigma grid, do they really understand or not? Because look what we've got. We've got an addition model to try to show multiplication. And if it really were going to show multiplication, you would have to do the 4 steps, wouldn't we? It'd have to be like Freddy the Frog. You'd have 4 jumps at 17.5, and then 3 jumps at 34.5, and that's not what is shown here. All right, so we can see right here that the student is lacking some conceptual understanding. I would have marked down more than 2. All right, I would have probably marked off 10 at this point because this really is significant. When we look at what do we do, however, we get an appropriate plan. And the student was able to express this in terms of complete sentences. We multiply 4 times 17.5 kilograms, 3 times 34.5 kilograms. We add them, well, then we add them, right? We focus on what they actually do. And they've multiplied. They get their answers, they add them together, and they did it, dang it, and they came up with an answer. They checked by doing the inverse operations. In this case, they checked the addition component by subtraction. They then checked the multiplication component by division. And as we go through and check, we would also want to make sure that we recognize they were not able to get the real understanding necessary because what they've drawn does not reflect the problem itself. Here's a couple more examples here. This is absolutely beautiful. You'll notice we got some fractions going on. So you would expect to see a fraction model. Well, look what we've got. I've got our old friend, the fraction cake, don't we? And so we have these fraction cakes. We have a good subtraction model that's being put in place using the number line. Remember your fact family approaches. We've got some good statements of fact. We have a lovely plan here. We subtract the time it takes to build the shelf from the time it takes to build the chair. If you look carefully down here, you'll notice they're using the equivalent form notions in terms of the fraction models. Again, a very, very nice level of understanding. If you want to go through it, you can take a look at this example as well. What I always find interesting about this is if you know about the area model, you can see what they're doing. They're using a portion of the area model. They're not drawing out the full rectangle, but clearly that's what's being indicated. And now you see the difference between this example and our earlier example. In this example, we show the 4 times 17.5, but look what that's referring back to. It's referring back to this area that's already been computed. So we see both components of mathematical modeling. We see the addition component, we see the area component. When we look at the student planning, we'll multiply 34.5 by 3 and then add it to the product of 17.5 by 4. And what I like about this that's kind of fun is look what they've done. They have drawn arrows showing their justifications. And so not only did they do it, dang it, but when they did their checks, they recognized that they are having to refer back. And so this is an easy one to check. Does the facts go along with the story problem? Well, you use your reading strategies to determine yes, it does. Does this picture go along with the facts, and does it represent an appropriate set of mathematical models? And it does. And in fact, these are models that we're very familiar with because we spent time this semester. We have the multiplicative model, we have the addition model. Is the plan sensible? Does it take into account the modeling and the data that we've gathered? And it does. So this is really nicely put together. It's important that you learn to start thinking beneath just the process, just beneath the rules. And what Polya and what problem solving in general tries to get us to do is to consider whether or not your answer makes sense. And so if we have students who can fill out a problem solving board effectively, you have what you need to make that first step in the Sigma grid. Did they get the correct answer? Yes. But you also have the second step. Do they understand? Because the research shows that if you can draw and describe what you're doing, it's highly likely that you also understand. This ability to think beneath the rules turns out to be extremely important. Otherwise, you end up with answers that sometimes don't make sense. For example, let's take a look at this. And I'm going to try to scroll this out a little bit at a time just to tease you, if you will, with what it is to think. Let's try to prove something rather interesting. We're going to set A equal to B. In algebra, we can do that all the time. We can set variables to whatever we want. So if A is equal to B, then A squared, which is the same as A times A, right, would be equal to A times B. Then we're going to subtract B squared from both sides. So A squared minus B squared is going to equal AB minus B squared. And then we're going to do a little bit of factoring here. And if this isn't familiar to you, I'm going to encourage you to practice it, because part of your content exams, when you go for licensing, will require you to do some simple polynomial factoring. And so, if you're not familiar with the difference of squares approach here, you need to review it. A squared minus B squared, I wouldn't lie to you, Pa, this is true. It's equal to A plus B times A minus B. If we pull out the B from here, we have B times A minus B. So now algebraically, you'll notice we have a minus b on both sides as a multiplying term. So we can cancel that out. And that leaves a plus b is equal to b. So that means since a is equal to b, then a plus b is equal to b plus b. So b plus b is equal to b. So 2b is equal to b. So dividing both sides by b, we get 2 is equal to 1. I sincerely hope that you're not happy with this. I'm hoping that this makes you realize, oh my goodness, if all I have done is just follow these steps procedurally, following what I remembered as algebraic rules, I got a problem. And the problem is that we don't understand where this is broken down. That's where this conceptual level of understanding pops up. I'm not going to leave you in a panic for too long, however. You notice we have a minus b and a minus b, and I said we'll cancel. Canceling is not a mathematical operation. I wish I could take that out of people's vocabulary. What you are really doing is you're dividing both sides by a minus b. And if a is equal to b, a minus b is equal to 0. And you may have recognized you just don't divide by 0. If you divide by 0, you have strange things happening, like being able to prove that 2 is equal to 1. There's a reason why some of these operations are set up the way they are, and why division by 0 is not allowed. There's a lot more to it than this, but this will at least kind of remind you of that as well. I want you to be thinking about some of these content considerations before you start getting ready to take your licensing exam. If you want some further reading on here, I'm including the initial chapter where we talked about the problem-solving board and used it in an initial study. This is where it was being used only as a data collection tool. Here in this particular chapter, I describe how you can use this in teaching. And then here's the Polya reference that you can use if you want to read further about it. What I think that you will find is that you will find that the problem-solving board will give you a really powerful tool, not just to remediate, but also for initial teaching of problem solving. You can use it for assessment. You can also use it as a way of teaching and keeping track of recording student work as they do it. Just like our fractions, it is both the object and the record of action when it's used appropriately. In the next video, we're going to combine these together and describe some classroom considerations now. And at that point, I'll give you my full prescription. How do you go about setting up a powerful mathematics classroom using what we know about student assessment, using what we know about using the problem-solving board to make that tough call between process and concept and how to teach it, and then finally using what we know about setting up an effective classroom that can be effective not only for you as a teacher, but more importantly for the students.